So let's take a closer look at this sheafification functor applied to the constant presheaf. And in this video, we're not going to be completely formal and rigorous. Maybe I'll come back to this once we've developed a couple more tools in a more rigorous way. But by the end, I'll have it set up that you probably could write down an isomorphism explicitly and prove it is an isomorphism of sheaves, etc. So recall that our constant, we've got some topological space X, and our constant presheaf is just going to assign every open set a copy of the integers. And this isn't a sheaf for stupid reasons, because the constant presheaf assigns to the empty set, by this definition, the integers again. And this should be the zero ring if we wanted it to be a sheaf. Okay, so not a sheaf for dumb reasons. So let's take a look at sheafification applied to the sheaf and see what we get. So as I wrote last time, the sheaf, if we evaluate it at U, this should be a ring, right? And it's a ring of functions from U into the disjoint union over all the stalks as X runs over U, subject to the condition that for any of the points in U, we should be able to sandwich some open set V between said point and U in such a way that there exists a section of our presheaf over V where for every point in V, the stalk of our of the section T should be equal to S evaluated at Z, right? So remember, S is a function. It takes values in the stalks at each point. So this condition is saying that S should not only at the point Z, it should take a value in the stalk at Z, which hopefully you agree with me that makes sense. And at least all over this whole open set, it should really just be given by the collection of stalks determined by a section. Yeah. So if we want to get a grip on what this thing actually looks like, well, first we should probably see what the stalks of our constant sheaf are, right? So the stalk of a constant sheaf at some point, remember this is the set of all equivalence classes U and T using different, not the same U and T as above, where U contains X and Z is a section of our presheaf over U. So really it's just an integer, right? And the equivalence relation on pairs says that U and T is equivalent to V and S if and only if T restricted to the intersection is equal to S restricted to the intersection, right? But if I have some, I don't know, an open set R and W, I'm running out of letters here, right? Remember our restriction map for the presheaf over W down to R is just the identity, right? This is a copy of the integers. This is a copy of the integers. My restriction maps are just the identity maps. So if this happened, right, the only way that S and T could possibly be equal upon restriction is if they had been equal before restriction, right? So it turns out in this case that S and T have to be equal, right? So these equivalence classes are really completely completely determined by the integer. So with this argument, you should be able to write down a ring isomorphism from the stock at every point to the integers. And so the map going one way is just projection. You just take the second factor here. For the map going in the other way, you could just take the pair determined by, so if you had some t in Z, you could just take the pair determined by the entire space, which is an open set, and T. So I think that should give you the inverse map, and then you go through the whole hassle of showing this is like a well-defined mutually inverse pair of ring homomorphisms, etc. Okay, so what does that mean exactly? Well, that means that we can think about the functions up here as really just being integer valued functions, right? Now, to be formal, we should still write it this way, but really what this condition is saying is that, oh yeah, each of these s, it's a function, it eats points at u, it spits out integers, and we're just keeping track of different versions of the integers, really. Great. Okay. Now we got to work out this other stuff. So maybe I can use the grab tool to copy this and bring it down. If it's going to be nice to me. Maybe this wasn't worth it. Okay, copy, paste, beautiful. Okay, I'll leave it as is. So I've got this other condition here. Let's try and unpack what it means. So I've got my little function, right? S from U to this disjoint union of these stalks, basically an integer valued function. And so here's my open set U. And I've picked a point Y, and I've sandwiched some other open set between these. And so this says there should exist a section T. Okay, so there's got to be some T, which again, just an integer, right? There's got to be some integer T, such that for all Z in V, okay, the stalk at T is equal to S at Z, right? So that means my function S, if I evaluate it at Z, what does it look like? Well, it's going to be the stalk of T, right? But the stalk of T is really just, I mean, it's completely determined by the integer T itself, right? So this is really going to be the pair of VT. And really, I could put any open subset of V here. As we just argued, the important part is really not the open sets for the constant presheaf. It's the integer T here. So in other words, this is constant, right? As I vary Z around here, if we look at the right side, there's no dependence on Z. Well, with the tiny sort of caveat that the dependence on Z is telling us which stock this is happening in. But no matter what stock we're in, we're taking the I should say germ. Sorry, the elements of the stock are germs. Sorry if that was confusing a little bit earlier. But so the point is the germ is the same. It's all determined by T. So if we're thinking about this, if we sort of forget for a moment that we're keeping track of our copies of Z and we're just thinking of S as an integer valued function, what this is saying is that S is constant on V, right? It's sending everything on V to the exact same integer. So in other words, this whole fancy sheafification condition just says we sum it up with the term locally constant, right? S is a function that's locally constant. So all that means is that around every point, there's some open set on which S is constant. So in this case, V would be the open set in which it's constant. And so this actually gives us, sort of inspiration for how else to write this sheaf down. So I'm going to write an a priori different sheaf. I don't know. Let me call it G. And so what is G going to be? G is going to be all U, which are functions, or sorry, it's going to be the sections of fancy G over U is going to be all sections, all functions from U to Z, where F is locally constant. Now I claim that this is not only a sheaf, but it is isomorphic as a sheaf to the sheafification of the constant presheaf. And I've effectively just argued this essentially in one direction, right? So from this whole thing here, we see how each of these S determines a function, can determine a function into the integers. The trick, perhaps, is maybe to take these locally constant functions, although this should be pretty straightforward. I'm going to leave it to you to do it, and figure out how to write them in this formalism. So that's basically it. So now we see what happens, right? We have our constant presheaf, not a sheaf. We see what happens when we apply the sheafification functor, at least up to isomorphism. What we get is just the collection of functions from open sets into our ring, which are locally constant. So that'll do it for today. See you in the next one.